So to differentiate z equals w to the 3 halves times quantity of w plus c times e to the w. And that's c.
Yes, so just making sure that I copied it correctly is w raised to 3 halves, and in parentheses w plus ce to w.
Yes.
Perfect. I refuse to work with this. I will distribute. So then I have it's w raised to 3 halves plus 1. 3 over 2 plus 2 over 2 is 5 over 2. And plus c, w to 3 halves times e to w. You can say, what have you accomplished here? You still have to use the product rule, yes, but it's only on these two and not on that. So I distributed w to 3 halves. Is that okay?
Yes.
Okay. So now dz over dw. I don't really like writing z prime, but it's okay. It's the same thing. I bring down 5 halves, and I subtract 1 from 5 halves. And when I subtract 5 over 2 minus 2 over 2, it's 3 over 2. W is the variable, the independent variable, so that's it for now. Plus C. You know me, I don't want to complicate things. I want as simple as possible. C is waiting outside. I differentiate now. This is the first function, and this is the second function. So this is a product. So I'm getting ready to write a sum of two terms. When I differentiate w to 3 halves, I bring down 3 halves. And from 3 over 2, I subtract 1, which is 2 over 2, and I get w to 1 half, and I have to copy e to w. So I differentiated the first function, I copy the second one, plus I copy the first one, and I differentiate the second function, is simply our best friend, one of our best friends, e to w prime is e to w. I am going to attempt, although I doubt that we can do anything, it's because of the c is in the way. I don't think we can do anything, but I'm just going to remove the bracket at least. So I have 5 halves w raised to 3 halves plus 3 halves c. You can change this into the square root of w e to w. And plus, I want to talk about this for a moment. So forget about this for just a couple of seconds. The whole thing. Just forget about it for a couple of minutes. So if I have, let's say, a w to 1 half, this is the same thing with the square root of w. Agreed? The numerator is smaller than the denominator. But if I have w raised to 5 halves, this can be further simplified. This is carved in stone because the numerator is smaller than the denominator. But here is the other way around. The numerator is bigger than the denominator. The denominator is smaller than the numerator. So when you take the integers out, 5 over 2 is 2 integers. So this can be further simplified. And if you understand this, or even, let's say, w to 3 halves, 3 over 2 is 1 integer and 1 half, then you will have no difficulties quickly, because sometimes this takes time, right? I don't want you to spend too much time on this. So 3 over 2, you take the integers out, and that's how you get 1, and the remainder is 1 half. The same thing here, 5 over 2, the integers that you take out 2, right? 5 over 2 is 2 integers and 1 half, and the 1 half is the square root. So keeping that in mind, and going back to our example, this is w, the square root of w, e to w. And this one is the same thing. So you can rewrite it as 5 halves w, the square root of w, and 3 halves c, w, the square root of w I meant to write, e to w plus w, the square root of w, e to w. There is nothing I can do here. because this one, these two are not like terms. They have WD, the square root of W both, but they don't, not both have e to W. So you could factor out if you wanted, but there is no need. But please remember this analysis. It will save you a lot of time. Every time, yes, Derek, you want to say something?
Well, is there an issue with writing instead of like W times the square root of W, just the square root of W cubed? This would just best without simplifying.
Yes, but that's not simplifying. Yes. So you have to simplify because sometimes this quantity will be in the denominator. Yeah. And if you don't simplify, in a second, Jet, if you don't simplify, sometimes you will not be able to combine like terms also. Yes, please.
So when you distribute the C, do you not put it on the right side because of...
No, I'm not myself today. Sorry. There was a very gentlemanish way of asking question. Thank you. Instead of saying, "Hey, lady, you forgot to distribute to both terms," he was very, very kind and gentle. He said, "Well, is that you mean that you don't have to?" Very nice. Thank you. Yes, Brian.
And so because the constant is being multiplied by W to the 3 halves times e to the W.
Yes, I'm using this rule. A constant times a function prime is the constant times a function prime. So the constant can stay outside, unless you forget to further go back and redistribute it, and that's a big thing. So please remember to distribute it to both terms, not like I just did. My apologies. Of course, there is a scene here. So please don't forget to distribute it. Thank you, Jeff. Okay, next question, please. Anything else? Very good. Anything else? If not, I would like to go back to 3.7 to other applications. Or we can stop for a couple of minutes so I can see how you differentiate few things. Which one? I'm sorry?
You said you were going to start going back to application.
Yes, 3.7. But I wanted to also give you a couple of examples to work on if you'd like.
Not graded, right?
Okay, this time, because it's the spring break next week. Okay, so let's say 28 on page 265. Y equals cosine x, everything raised to x. And then 34, same page, as y equals 10 raised to tangent. I think it's pi x. Yeah, it's theta, but by mistake, I changed it into x. Okay, so let's work on these two. 2 minutes. Okay, 1.5. I'm kidding. Randy looked at me and said, really, 2 minutes? Let me know when you're ready with the first one. Anyone needs help with anything? So can anyone get us started on this one? What do we need to do? Because there is no rule, differentiation rule of a function raised to a function.
Natural.
Yes, we have to apply natural log to both sides so we can bring x in front as a factor. So when we apply natural log to both sides, we will bring x in front as a factor. So let's start with that. Is that clear, everyone? So that would be the first step. Anyone needs help? Should I turn this on? So we will write a natural log y equals x times natural log cosine. How are we doing?
Check the,
The formula for the differentiation for cosine for natural log?
yeah.
Okay, so natural log prime is 1 over that expression times the expression prime. So let me write it down for you. So natural log of a function prime is 1 over the function times the function prime. So yes, that's correct. And then you have to differentiate. But don't forget to put x in front though. Because you have to differentiate. No. So this x goes in front of natural log. And we have to use a product rule. How are we doing? Okay, that's perfect. Yes, but don't forget to put in parentheses. Yes, because of the negative sign. No. The negative sign and the multiplication. So that's why we have to separate them. There are two operation symbols. I cannot have a product and negative next to each other. So if we have something like this, for example, x negative sign x, it appears that it's a subtraction. But if I put in parentheses, it's very clear that it's a product.
Okay, gotcha.
Is that clear?
Yeah.
Okay, perfect. So because it is a product. Maybe how we do? Yes, but we have to differentiate as a product, and we have to have a sum of two terms. So we have x prime, which is 1, times natural log plus x times natural log prime using this formula. Am I working? So we'll do this together. How are we doing?
Stuck.
If everyone is stuck, then it's my fault. I mean, if everyone is stuck, then obviously it's my fault. How are we doing?
So we got to there. Yeah.
Right, but that's not the product rule. Remember, when we apply the product rule, we have to we have to have a sum. Don't forget dy by dx here. Y is a function. So when we differentiate the function that we don't have, it's 1 over y times dy over dx. So no, right here, it's 1 over y times dy by dx, not alone 1 over y. Oh, okay. But the 1 over y has to be put in front, however. It's not a mistake, I understand it's the same thing, but we have to put it in front, yeah. Yes. X, yes. Okay, so now, see, you can change this if you like into negative tangent and put a minus in front, because there are too many parentheses, it looks too heavy. I'm not saying it's wrong, it's not wrong. How are you doing? So we have 1 over the y, yes, 1 over y divided over dx. Is that okay? So 1 over y divided over dx, and that's 1 over, yes. And I don't see a sum. I have to see I have to see a sum of 2 terms whenever you apply the product rule, correct? So a sum of 2 terms. So I don't see the sum. So what happened to natural log cosine x? Where did it go? Yeah, but where does the natural log cosine x go? Okay, hold on 1 second. What are we doing? You're on the right track, however. Everything you did was good. So, okay, so I'm not happy. When I'm not happy, I cry. Okay. But I try not to do it because then the people outside will call the security or something. So who knows? Her students are torturing her. Come over. Okay, ready? So we have y equals cosine x raised to the x power. Agreed? We apply natural log. So let's take it slowly. Natural log applied to cosine raised to the x power. Correct so far? At this point, that is the whole purpose. To bring the x in front of natural log. So this is natural log y equals x times natural log of cosine x. Agreed? This is function 1, and this is function 2. So far, so good? Okay. Now the left-hand side, when we differentiate, we don't have this function. You can say it's right there. Yeah, but I can differentiate it. So it's a function I don't have. So I have to write 1 over y times the inner function prime. I'm using this. 1 over y times the inner function prime, but I can't write that. I have to write dy over dx. Is this okay so far on the left-hand side? We agree? But now the right-hand side has to have a sum of 2 products or 2 functions. So when I differentiate the first function, I get 1, so I just copy this. Plus, when I differentiate the second function, I have to copy the first one. And I use the same rule, 1 over cosine times cosine prime, which is negative sine x. So 1 over cosine multiply by negative sine x. Please put parentheses between the negative sign and the product, because otherwise it will appear that to be a difference instead of a product. So now 1 over y dy over dx, I just want to change this. I can already multiply by y. So it's a natural log of cosine x, and this is minus x tangent x. Do we agree with this?
Parentheses on the right?
Negative sine x, the inner function prime. Sorry, of course, I ran out of room. So all I have to do now is multiply both sides by y. But this is y. So all I have to write as the final answer is that dy over dx equals cosine x raised to the x power times all this. Natural log of cosine x minus x tangent x. And this is final. What part was confusing, bless you, or not clear, or needed help? Please, Brian.
I forgot that the natural log of the function.
Prime.
Derivative, yeah, so is equal to 1 over f times the function prime.
Okay.
I missed the function prime.
Yes.
I remembered 1 over
So
f.
only natural log x prime is 1 over x. That's it.
Yeah.
Because that would be times x prime, which is 1.
Right.
But if it's anything else inside of natural log, you have to use 1 over that times that prime.
Yeah, I forgot. I thought it was 1 over the function prime. So that's how
No. It's 1 over the function times the function prime. Good. Are we working on the other one? Any other questions? Other questions on the previous one? Did we learn from our mistakes? Yes? Okay, perfect. That's the whole purpose of the exercise. Which differentiation rule we need here? What if this were just e? What would the answer be if this were e? Times secant squared pi x times pi. But it's not e, it's 10. So at the very end, I need to multiply by natural log 10. So if it were e, I want to multiply by natural log e, because natural log e is 1, I don't have to. So let me refresh your memory on this. These are the differentiation rules. We need to remember them, okay? So a raised to a function prime is a raised to the function times the function prime times natural log a. If we have e to the function, we have e to the function times the function prime times natural log e. But there is no need for this. Why? Because it's 1. Okay, almost done with that. So then y prime or dy over dx equals, one more time, can anyone dictate?
Ten to the tangent 5x times secant squared 5.
Yes, times pi
Oh,
times natural log 10. Don't forget the inner function prime. This pi would have not been there if the argument of tangent were just x. But the argument of tangent is, it's a function of x, it's pi x. So then I have to further differentiate. So remember to start from the outer to the innermost. So this is the outer, e to something. Then this is the next. Then this is the next. And then because this is not e, I have to multiply by natural log 10. Is this okay? Questions? Questions?
you wouldn't want us to evaluate 5 times the actual natural log of 10.
You cannot multiply anything here. No, I don't want this. No, don't touch it. I want the exact. No, no need. Okay. So I'd like us to continue with any questions, by the way? Any questions? Any questions? I would like us to continue with 3.7, more applications. But I want to talk about the following scenario. Before we look at a problem with a marginal cost, I'll explain what that means in a minute. So here's a function, f of x. I need this idea now, and we will revisit it in section 3.10. Okay, so I have a point, P, of coordinates, of course, x and f of x. And I have another point, let's call it Q. And the coordinates of Q are x plus. Very good. I'm going to call this, instead of tiny h, as we did, it's the same thing, just different notation, bear with me, delta x, or x plus dx. In other words, this piece is the same, delta x is the same with dx. And of course, the corresponding y coordinate of Q, it doesn't matter which one I use. I'm going to use dx. So it's f of x plus dx. Of course, this is a minor change. Minor change in x. In other words, I'm telling you P and Q are quite close. Derek, you had a question? Okay, so P and Q are quite close. I'm going to form a right triangle by drawing the tangent here and extending it. So I hope you agree that this is a right triangle. I have a horizontal at P, which is f of x. In other words, I drew the tangent at P, and I formed the right triangle right here. Obviously, this piece is dx. This piece we're going to talk about in a minute. We don't know what this is yet. But I definitely know this. Can anyone express that piece in any way? Forget about the green triangle. I just have this point, which is Q, and this height is f of x plus dx. I have this point P, and this height is f of x. And now I'm asking, what is this? Say it again. No. No. So, of course, is this height minus this height? Do we see that? Okay, so this is f of x plus dx minus f of x. Okay, so here's what I'm telling you, and you tell me whether this is clear. When, we don't have to write it like this, I just want to clarify it. When there is a minor change, like an error if you want, in x of dx, that's the minor change, or the error if you want. Call it the way you like. That triggers a in f of x. Triggers a what? Yeah, maybe minor or not, but definitely a change, right? And now I'm asking you, what is the exact change in f of x for a change of dx in x? What does this equal to? Right, absolutely, no question. Plus dx minus f of x. This is called delta y. It's the exact change, the exact difference in the function triggered by a change in x. Now I want to come back to the green triangle. We have not used the green triangle yet. So we have a change in x, obviously from P to Q, from P to Q. So then the exact change that is triggered by dx in the function is this. Because to get from P to Q, this is the rise, and this is the run. Perfect. Now, forget about f of x plus dx minus f of x. And let's look at this triangle. And I'm going to remove it from there, because I need to explain something. So I'm going to graph it here. Here is point P. This is already known to be dx. This is not known. We don't know what that is yet. But I would like you to give me the slope of the tangent line at P. Forget about the graph right now. Forget about this graph for a second. Just tell me from there, what is the slope of the derivative at P equal to? Much easier than that. Say it again.
Inverse of f of x.
No.
Derivative.
Yes, of course, it's f prime of x. Of course. So if this is 5, then the slope of this will be f prime of 5. If this is x, the slope of this will be f prime of x. Agreed? Everyone? Okay. So this is f prime of x. And now, tell me the slope of this line in a different way. You will have to say rise over, but these two have to be the same. The slope of the tangent line is the steepness of the line here, and it's f prime of x carved in stone. Now from this triangle, right triangle, I should have put there so you can see that that's a right triangle, of course. It's the green triangle from here. Obviously, the slope of this line must be rise over run. But these two must be the same. There is only one slope for this line. So f prime of x, this, must equal this. What is the only thing that fits in here? Because we've been using this notation for a long time. However, I wasn't completely honest with you. I didn't tell you that this and this have separate meanings as well. I only said here, f prime of x can be replaced by this, but I didn't tell you that each piece has a meaning. But I will tell you now what fits up there. Of course, there is nothing else. So therefore, what is this piece then? dy. What does dy represent? dy represents the differential. The x also represents the differential of x. I have not looked up how this word was or came about, but I think it's two words put together, difference and derivative. So they put them together and said the differential. That's what I think. I don't know. I have to do some research. So differential of y means the change in y. But it's the change in y using the derivative. Is not the exact change in y. Is the change in y that is not identical with delta y, but is the change in y using the derivative or the slope of the tangent line at point P. However, imagine that this is zoomed in, right? And we know that Q and P are very close to each other. What will be the relationship between delta y and dy? You cannot say equal because they are absolutely not equal. But what will you say the relationship between these two? Between the exact change in y using f of x plus dx and f of x, and the derivative or the slope of the derivative, or the slope of the tangent or the derivative, same thing, at p. What will be the relationship between these two? And no, you don't know which one is higher or lower. So it's not an inequality. It's not the equal symbol. What can it be?
Yes, it says delta y approaches 0 and they'll be the same.
So they are approximately equal. They are not equal. And we don't know which one is larger. One or the other could be larger. So this piece, which is the exact difference triggered by a minor error, we'll have plenty of examples and problems like this. This is the exact. We don't really want to calculate it. It's cumbersome. And if we are happy with a minor error, we will always calculate this. Again, this is zoomed in. Q is very, very close to P. So then delta y and dy are extremely close. It depends on the x. If you say dx is 5, then they're not going to be close. But if you say dx is 0.3, they will be very close.
Does the area of that triangle mean anything to us, or was that
No.
just part of walking into it?
Yes, I only needed you to understand what this piece means. So I determined the slope of this, but also from in any triangle, the slope of this line is rise over run. And they have to be the same. And if they have to be the same, the top must be dy. There is nothing else. So then moving forward, and you're going to see this again, we will write that f of x plus dx minus f of x is approximately dy. But I want you to solve this equation for me for dy. What will you do to that equation? And you can say, yeah, I didn't know that you can separate them. Yes, because they have special meanings. So how much is dy from that equation? Yes, but we will have to write it f prime of x dx. Does it matter? No. Is it important moving forward? Very. To remember f prime of x dx. But if you write them like opposite, using the commutative law, it's fine. But we don't do that. So then it's f prime of x dx. And depending on what I need, normally we will solve for this. I'll show you applications in a minute, in which we're going to move f of x to the other side. So this is f of x plus dx, approximately f of x plus f prime of x dx. Get used to this moving forward. This is another major result. S major as continuity at the point is. Okay, so here's our first application of this concept. Okay, one more time, what did we do? One more review, quick review. We said all of a sudden, let's say, we want to manufacture disks. And we're not capable of manufacturing disks of exact, all the same diameter or radius. They have a minor error, but we're fine with the error. Let's say plus or minus 0.1 inch. We're fine with that, plus or minus. So the radius can be plus or minus that error. That is our dx. However, we are interested in this minor error. What error will it create in the area of the disk? For whatever reason, that is our function. The function is the area of the disk. So if we increase or decrease the radius by a little bit, how much will the area increase or decrease? So if that's the case, this is the exact change. F of what the radius should be plus the error minus f of the radius. This will give us the exact error in the area. However, if I want a quick result, and I don't want to stress over this because I can live with a little bit of error from the actual answer. I mean, if it's medicine and life-threatening situation, then I don't want any error. But if it's allowed some error, I would rather determine that error using this, f prime of x dx. It's just the product, f prime of x dx, and I'm done. I don't need to calculate this. I don't need to calculate that. I only calculate f prime and multiply by the error of dx, and I'm done. It's much easier than this. But again, delta y and dy are not identical. Okay, so now let's apply this. This is the first very simple example concerning marginal cost. Okay, so the cost in dollars of producing X yards of a certain fabric is blah, blah, blah. Find the marginal cost function. The marginal cost function is C prime. It's called marginal cost. Instead of the derivative of the cost, it's called the marginal cost. Fine. Find C prime of 200. Okay, and explain its meaning. Fine. What does it predict? We'll explain that too. Compare C prime of 200 with the cost of manufacturing the 201st yard of fabric. So I want to manufacture 200 first, and then I want to manufacture 201. So does this sound familiar? I want to manufacture 200, but then I want to manufacture 201. How much is delta x or dx in this case? 1. So I want to see the difference in the cost. So I can plug it in the function and say C of 201 minus C of 200 and get the exact cost of manufacturing the 201st item. Or I can say, wait a minute, I am going to determine C prime of 200 because C prime of 200 will predict, because it's 1, because dx is only 1, right? So C prime of 200 times 1 will give us the difference. C prime of 200 times 1, because that's dx, will give us that prediction. Instead of having to determine the exact delta y, I will just plug in f prime 200 multiplied by 1, and that's my prediction. I don't have to go through all this. And we will show how close they are. No, because f of c of 101 minus c of 100 is not going to be exact with f prime of 200 times 1. But they will be very close. Why? Because the exact change in the cost for manufacturing one more will be very, very close to f prime of 200 times 1 from this relationship. So let's start slowly. Let's copy the function first. So that is problem 31 on page 236. And this is c of x. And of course, I don't like the way that it's presented. It's not in descending order. It bothers me. 5x cubed minus 0.1 x squared plus 12x and plus 1200. First question is asking us, first part is asking us to find the marginal cost. Marginal cost. That's not a problem. C prime of x, I bring 3 down and I get 0.0015 x squared minus 0.2x plus 12. Do we agree with this? In part B, they're asking us to find C prime of 200. Okay, so let's do that with a graphing calculator. In y equals, let's punch it in because I may want to go back and put in something else. I don't know. So 0.0015 x squared minus 0.2x and plus 12. Do we have the function in? And then we go to second and table, and we want to plug in 200. And I got 32. You don't have to go to the right, but because it appears that this is it. So I got 32. What is 32? Measurement unit. Remember, this is a rate of change. So I need 2 measurement units. If it's a rate of change, it's a ratio. So I need 2 measurement units. The rate of change, very good, per yard of fabric. Excellent. It predicts, that's our claim right now, it predicts the cost of the 201st yard of fabric. And this is a statement that you should say, show me, and I will. Okay, so how did we get this? We got this from C prime of 200 times 1. This is dx. And this is our 32 per yard of fabric. Now in part C, it says, compare C prime of 200, which we just determined to be 32, with the cost of manufacturing the 201st yard of fabric. Remember what does that mean? So this is 200 and this is 201. So I have to find f of 201 and subtract f of 200. 200, 201, right? F of 201 minus f of 200 to determine the exact cost of the 201st item. Okay, let's see what happens. So delta y is C of 201 minus C of 200. That's the exact. This is dy. Our claim is, like for every function, that dy is approximately delta y is approximately dy for small dx. Because if you tell me that the x is 10, then delta y and dy will not be close to each other. But if the x is small, then delta y and dy will be close to each other. Okay, how do I determine this? Let's go back to the calculator, and please plug in the second function the original function, 0.005x cubed and then minus 0.1x squared. And then plus 12x, and then plus 1200, I think, yes. And then go to second and table, and also plug in 201. The red function is the cost. The blue function is the derivative. So the cost of 201 is 3632 point, and I'll see in a moment. The cost of 200 is 3600. What's the difference?
2.2.
The derivative at 200. So let me copy, first of all, let me see what this gives us. Okay. So I copy 3632.205 and I subtract 3600 and I got 32.2005 dollars. So to manufacture, according to the function, 200, I pay 3,600. To manufacture 201, I pay 3,600, 3,632.2005. But that means that the difference is the cost of the 201st item, which is 32.20005. Which of these two procedures was easier? Was it easier to determine? Yes, we have calculators, yes, we have computers and software, I understand. But in principle, was it more cumbersome to determine this or to determine this? C prime, I had C prime, I put in 200 multiplied by 1 and I'm done. It's the mechanism that I'm talking about. Yes, Eric, go ahead.
How do I know, like, depending on the context, what is sufficiently small delta x so that this value is correct? Because in here you said 1 is okay, but if I use some instance where the numbers are generally quite small, 1 might be quite large. So
That's what I said. It depends on how much error they normally should be close. As long as delta dx or delta x is small, yeah. But it's a very good question. It depends.